this pre-calculus algebra video, we will walk through the properties of logarithms. If you're studying logarithms in your algebra course, then the first step is to understand these basic properties, to understand what is a log. So in general terms, a log is used to find an exponent. And from the different properties we have, if you have the product rule for logs, we can find log base 5 of 7 times 3. Log base 5 of a product is equivalent to the sum of the two logs. So the log of a product is equivalent to the sum of two logs. That's the product rule. So if I have log base 5 of 7 times 3, I can rewrite that as log base 5 of 7 plus log base 5 of 3. So applying the log properties, the first property here, the product rule, is that we can switch from multiplying the log of two things being multiplied is equivalent to the addition of those two logs. Notice that the base has to be the same, so it's log base 5 in both cases, log base 5 of 7 and log base 5 of 3. We could also very similarly use the quotient rule. The log of a quotient is equivalent to the difference of the two logs. So I could rewrite this log as log base 4 of 64 minus log base 4 of y. Notice that this does have to go in order. It's the numerator comes first, log base 4 of the numerator, minus log base 4 of the denominator. So make sure you're putting those in the right order when you use the quotient rule. By the way, if these things seem new to you and you haven't watched the video on log properties, I'd encourage you to stop the video and go back and watch the video on the basic log properties first. I think that would really help you. This next one is really important when we come to solving equations. So mark this one with a big giant red flag or star, or draw a pretty flower, something to alert yourself in your notes. Highlight it, that this one's exceptionally important when we're solving equations especially. But here's how this one works, the power rule of logs. What happens is when we have log base b of this value x raised to a power, so nice, it's like ripened fruit on a tree. It just falls right off. It's just ripe to fall. You don't even have to pick it. It just falls right down to the front. So log base b of x cubed is going to be equivalent to 3 times log base b of x. So when we have an exponent here, it just falls down in front. That's a really important one. Mark that one. We're going to use it often when we do some work with solving equations. We could use the power rule to expand log base n of negative 6. I'm sorry, not log base n. This looks like it's a log base 10, doesn't it? Log base 10, because it's a common log. When we have a log and there's no base written in, it's implied that the base is 10. So we call this that common log. So when we have this log of n to the negative 6 power, then what we can do is simply bring that negative 6 down in front. So this negative 6, when we have the exponent, just falls right in front. So log of n to the negative 6 is equivalent to negative 6 times, I don't even have to write that times sign down, but that's the operation we're doing though. Negative 6 times log base 10 of n. That's the power rule. Let's look at another example. Use log properties to expand. If we're expanding then we're going to use the uh, product or quotient rules. Let me start by rewriting this fifth root of x. So just a quick review, the fifth root of x, that's the same as saying x to the 1/5 power. That's not anything to do with logs. This is just by definition when we have a radical with an index that we could rewrite it as that base, the x, in the radical form, the radicand, raised to a rational exponent. So just by definition, fifth root of x is the same thing as saying x to the 1/5. So let me rewrite this that way. Natural log of, instead of fifth root of x, I'm going to write x to the 1/5. What I could then do is I could rewrite this, bringing that 1/5 down. This says use log properties to expand. It doesn't tell me which property to use, but I need to know that, oh, when there's an exponent, I'm going to use this power rule that says that the power, the 1/5, falls down in front. So we get 1/5 natural log of x. 1/5 log base e of x. When we say ln, what we're saying is log base e. And then log base b of x squared y, we could use the product rule. We can see this is the log of a product. So we could expand it to log base b of x squared plus log base b of y. But wait, there's more. Did you see that we had this exponent? Did you notice that there was this 2 here? So we could expand this just a little bit further by saying that this is 2 times log base b of x plus log base b of y. Let's look at number 5, or 4c rather. We could expand log base 6 of negative 36 over the square root of x plus 1. And to start with, let me rewrite that radical. So the square root of x plus 1 is equivalent to, if I rewrite it with exponents, I'd use the rational exponent 1/2. There's an implied 2 in this radical because it's a square root when it's not noted otherwise. So the square root of x plus 1 is equivalent to x plus 1 raised to the 1/2 power. If I wanted to expand this, I could see that the log of a quotient is equivalent to the difference of the two logs. So I could rewrite this as log base 6. I think I initially missaw this. I misread this. I think I initially thought that was a negative, but that's just one long fraction part. There's no negative there. So log base 6, if you look at the bigger printout of this, you probably notice that it doesn't say negative. It's just that fraction part. So we'd have log base 6 of 36 minus log base 6 of the square root of x plus 1. I'm going to write that log base 6 of x plus 1 to the 1/2. Well, that's our first step, but that's not all, because we can simplify this log base 6 of 36. What we're doing to simplify that is we're saying, what exponent would I raise 6 to get a 36? And that's a basic square, so we should be able to see that, oh, well, it's 6 squared. 6 squared is 36. So log base 6, what's the exponent? This log base 6 of 36 is saying, what exponent would I raise a 6 to, 6 as the base, to what exponent would equal 36? And that answer is 6. So I should simplify that to a 6. We'd have, or I'm sorry, not a 6, simplify it to a 2. Log base 6 of 36, 6 to the second exponent, the missing exponent is 2. So log base 6 of 36 is 2. 6 squared is 36. So log base 6 of 36 is 2. So we have 2 minus, and then I could use the power rule to bring this 1/2 down in front. 2 minus 1/2 log base 6 of x plus 1. I'm going to keep that x plus 1 in parentheses to clarify that it's not log base 6 of x. Without the parentheses, it would look like this, where it would be interpreted as log base 6 of x plus 1. That's not what we're doing, is it? What we want to do is the log of the entire radicand, the entire x plus 1. So make sure you've got those parentheses on the x plus 1. Moving on to number 5, write as a single log. Now we can go in reverse. If the log of a product was equal to the sum of two logs, then we could say that the sum of two logs is equal to the log of their product. So we could write this as log base 10 of 5 plus log base 10 of 2, or the common log of 5 plus the common log of 2 is going to be equivalent to log base 10 of 5 times 2. Wait, where did I get that 10? Well, that's by definition. When the base isn't written in, it's implied to be a 10, and it's called the common base. And then the log of that common base is the common log. So log with no base written is implied log base 10, and it's called the common log. So log base 10 of 5 times 2, or just log of, and now 5 times 2 is 10. And do you see how we could simplify this further? If I understand, so if I didn't know that common log meant base 10, I'd just be done here. I'd be done and I'd put a box around it, right? But I know that that means log base 10 of 10, so I could go a little bit further here, because 10 to what exponent equals 10? So this log 10 is okay, but it's not the final answer, because 10 to what exponent equals 10? Did you say 1? That was correct. Yes, the log of 5 times 2, the log of 10, is going to be 1. You see how these are working? With a little bit of practice, you can get really good at this, but you're not going to get it down completely by watching me do it. You really need to jump in and do some of these yourself. Let's work backwards from the quotient rule. So if we have the difference of two logs, we could then write this as a quotient. And this 4 down in front is going to be an exponent, right? But let's just start with a quotient. We could say that if we write these as a single log, 4 times the natural log of x plus 6 minus 3 times the natural log of x is going to be 4 times the natural log of x plus 6 divided by, so this minus, when we have the difference of two logs, is going to be the quotient. So 3 natural log of x. Then we could go a little bit further here. We could go a little bit further and we could take this exponent and put it up top. So we'd have the natural log of x plus 6 raised to the exponent of 4 divided by natural log of x cubed. Now these are the same base, so I could say that this is going to be equivalent to let's move on to 5b. Here we're going to go from difference to a quotient. So if I have the difference of two logs, I could rewrite that as a single log of their quotients. Before I do that, though, let's use the power rule to rewrite each of these as, so this 4 natural log of x plus 6 is going to be the natural log of x plus 6 to the 4th power, right? So the 3, same thing, I could write this 3 in as the exponent. So minus the natural log of x cubed. So I'm going backwards from the product rule. If I have some power times a log, I could write that as the log of base, the same base, and then I could write that coefficient that came out in front of the log as the exponent, the power. So I could start with this, 4 times the natural log of x plus 6 minus 3 times the natural log of x is equivalent to the natural log of x plus 6 raised to the 4th power minus the natural log of x to the 3rd power. Now, because I have the natural log, it's the same base, log base c, I could rewrite these as a single quotient. So I could say that the difference simplifies to, or condenses down to, the natural log of x plus 6 all to the 4th over x to the 3rd. That's writing as a single log, or condensing. I started out expanded and then I condensed it. Now here we go with one where we're going to have both a quotient, because we have a addition, and a product, because we had addition, and a quotient with the subtraction. So as we condense this down from its expanded form, we're going to get a sum and difference. So we're going to have a product and a quotient. Let's look at how this would work. One way to see it is that anything that's added, anything that's positive, it's a plus. So plus 3 ln x plus 5 ln y is going to go in the numerator. And anything when we get a subtraction, when we subtract 6 ln z, that means divided by. So let's start by using the power rule. I could say that this is the natural log of x cubed plus the natural log of y to the 5th minus the natural log of z. I'm going to draw a line through my z so it doesn't look like 2, minus the natural log of z to the 6th power. That's the first step. And now as I rewrite this as products and quotients, we have natural log of x cubed times y to the 5th and then for the subtraction, when I do subtract the natural log of z to the 6th, that means the z to the 6th is going to go in the denominator. Again, one way to see this when we have a series of sums and differences, anything that's positive, anything that's being added is going to be in the numerator, and then that piece that's subtracted is going to be in the denominator. I hope that helps you see how to approach this one in the future. But we'd get the natural log of x cubed times y to the 5th divided by z to the 6th. Let's look at number 6. We could use common logs to evaluate this on a calculator. Our calculator doesn't do log base 1/10, but we could rewrite this as a log base 10. Here's how it would work. Log base 10 of 17 divided by log base 10 of 1/10. And then what I could then do is put this in on my calculator, and I'm going to do this with a Texas Instruments 30X. I simply find the log button. Log, it opens up a parenthesis for me, so I type in the 17 and close a parenthesis, and then divided by log, it opens up the parenthesis, I'll type in the 0.1 and close a parenthesis, and that gives me a result of negative 1.2. Now I'm not going to say this is equal, but it's approximately 1.230448921. And it actually would keep going and going and going. It doesn't end. If I'm going to round this to, let's say, 4 decimal places is usually acceptable. If I'm rounding this to 4 decimal places, to get really good at rounding, right? If I round this to 4 decimal places, I could say 1.2304. Let's try the with the same log, but with base e. I could write this as log, I could use any base I want, log base e of 17 divided by log base e of 1/10, and that is log natural, ln. This log base e means log natural or natural log. So the natural log of 17 divided by the natural log of 0.1. And lo and behold, when you put that in on your calculator, we're going to get the same result. So it's approximately 1.2304 still, right? The log base 1/10 of 17 is going to be the same whether we change it to a natural log or to a common log. And that wraps up what we needed to do here. Oh, wait, let me just write. You know what? That was a negative, wasn't it? On the calculator, it said negative. I just didn't write that negative. I apologize for that. Hope you caught that it, on your calculator, it should say negative. My calculator said negative, but it had a glare in it with this light above me for the video, and I overlooked that negative. Here's all the properties put together for you. You'll need to be very familiar with all the properties. If you haven't watched the video that walks through each of these properties, I'd encourage you to rewind and go back to that video and then maybe watch these examples worked out again. Logs are not really difficult if you get the practice in. It is something new for most students, so you need to practice it a bit to get to where you can work with the different examples of logs. I hope that this video has helped you get started with that study.